Section 7.1 Integration by Parts. To begin, every differentiation rule has a corresponding integration rule. For example, the substitution rule for integration corresponds to the chain rule for integration. The rule that corresponds to the product rule for differentiation is called the rule for integration by parts. Recall the product rule. So our product rule says that if we have two arguments or two functions of x, and to take the derivative, we take the derivative of one times the original function plus the derivative of the other times the other original function, right? So for integration, we have to undo the multiplication and the combination of terms that we did when we're simplifying at the end. So for the notation for indefinite integrals, this equation becomes the integral of f of x times g prime of x plus g prime of x plus times f prime of x dx equals f of x times g of x. Or the integral of f of x times g prime of x dx plus the integral of g of x times g prime of x dx, which equals f of x times gx. So our formula for integration by parts is just like listed above, but we have a process that we use for integration. We like to use substitution in our integration by parts. It is sometimes easier to use the following notation. Let u equal f of x and v equal g of x. Then the differentials are du f prime of x and dv g prime of x. So by the substitution rule, the formula for integration by parts becomes the integral of u dv is equal to u times v minus the integral of u du. When deciding a choice for u and v, we usually try to choose a u equals f of x to be a function that becomes simpler when differentiating. It's not always so, but that's what you have to keep in the back of your head. Or at least not more complicated, as long as dv minus g prime of x can be readily integrated to give v. Alright, so let me give you a little guide. So as you're working with this, for one function, you want to go ahead and start, and your goal is to take the derivative a bit. And then your other function, you're going to work backwards and integrate. So I usually draw two arrows going down, one going down to show differentiation, one going up to show integration. So we're going to label one of them to be u, and then our other function will be dv. And for one of them, we're going to integrate with the hopes of getting our v, right? And then for the other one, we're going to differentiate. With the goals are finding our derivative, du. And don't forget that dx for the partial derivative. All right, so this is our setup. Now our goal as we're working through this is to find out what our u is, find out what our v. Once we have them settled down, we want to take our derivative and then our integral, and we just plug them into our formula. Now in one of the examples, I'll show you an alternate method, but the alternate method doesn't always work. But this differentiation by parts using u substitution works most of the times. All right, let's do an example. Find the integral of x times sine of x dx. Okay, so we see that x is kind of the simpler one. So that's going to be the one we take the derivative of. So we're going to set u, we're going to take a derivative of this one. So we're going to have u is equal to x. And now the other one is going to be the one that we integrate for. So we're going to have dv is equal to sine of x dx. Okay, now we have every part of our function labeled. Let's go ahead and actually apply the derivative and the integral. So our derivative, our partial derivative, gives us du is equal to 1 dx. And for the other one, we're integrating. So if we're integrating, that's going to give us v is equal to, well, the integral of sine of x is negative cosine of x. Okay, now that we have everything listed, let's go ahead and use our formula. Now to begin, I highly emphasize use your formula because your formula will keep you from making silly mistakes. Okay, so our formula is, and we have it right above too, our formula is the integral of u dv is equal to u times b, and is the integral of b du. Okay, let's go ahead and find these replacements. So we have u as x, so we have x. Our v is negative cosine of x times negative cosine of x minus our integral of v. What is our v? Our v is negative cosine of x. And what is our du? Our du is just dx. All right, now we have set ourselves up for our first part. So if you got this far, you're in good shape. Okay, but you see, we still have another integral to work with. This here. But that's an integral we can easily find, right? We see that to integrate, the integral of negative cosine of x is just negative sine of x. So putting it all together, our answer is x, negative x cosine of x, and negative negative makes positive, sine of x. And because it's an indefinite integral, don't forget your plus c. And this is integration by parts. Now, I was looking online to see if there's any tricks to help us keep track of which one should be our u and which one should be our dv. So which one should we differentiate and which one should we integrate? Now with practice, I'm sure you'll develop a sense of it, but a trick is, remember this phrase, and this tells you whichever comes first should be your u. So L stands for logs, I stands for inverse trig, like sine inverse, cosine inverse. A stands for algebra, like an algebraic expression. T stands for trigonometry, like sine, cosine, tangent. And E stands for exponents. So again, the first one, that's a little star. The first one you have in your problem should be the u. Okay, let's do a problem here. So we have ln of x dx. So to help us set up for integration by parts, we need to have something to be our u and something to be our dv. Let's rewrite it to be ln of x times 1 dx for our integral, so that we can see them as two different things. For this one, we're going to let u be ln of x, and we're going to let dv be 1 dx. Now remember, for one we're going to be integrating, for the other going to be differentiating. So for our first one, we have u. Our derivative, our partial derivative du, would be du is equal to 1 over x dx. And our integral would be b equals x. The integral of 1 is just x. So we have v equals x. Okay, let's go ahead and use our formula to fill out these pieces. So we have, our formula is u times v minus the integral of v du. So let's fill that out. Our u is ln of x. Our v is x. Minus the integral of v, which is x. And du is 1 over x dx. All right, well, what is x times 1 over x? That's just 1, right? So we have so far is x ln of x minus the integral of 1. Well, if we're taking the antiderivative of 1, that just takes us to the variable x. So we have x ln of x minus x. Don't forget your plus c, since we have an indefinite integral. Now, an alternative method you can try, though it doesn't work for all situations with differentiation by parts. In the next example, I'm going to show you what's called the tabular method. And this one's nice because it kind of lets you do things a lot more quicker. But the only problem is you might be in a situation where you can go in a never-ending circle of integrals and derivatives where it never ends. And for such problems, if you find yourself in a situation, you can just go back and use the formula, like we'll see here. This one is a very bad tabular method problem because you'll just go in circles and never finish. Okay, so let's take a look at the example right above. Find the integral of t squared times e to the t dt. Well, just to recall our formula, we have our formula for differentiation by parts is the integral of u dv or du is equal to u times v minus the integral of v du. So we see here our first term is positive, our second term is negative, and it's going to continue that pattern so that the next term would be positive and then negative and then positive and negative. So with the tabular method, you want to keep track of our signs. So we have positive, because our first term should be positive, then negative, and then positive and negative, and so on, however many we need. Next, in our tabular method, we're going to label our derivative part, our u. So what function should be the one we work with the derivative? We're going to have some u is equal, right? And then next we have whatever function should be our integral. Our dv. All right, so we need our signs, derivative, and integral. Now, this is just a way to keep track of all the integration and differentiation that you would have to do to be able to complete integration by parts. All right, so we're going to label u is going to be the simpler one, right? So here our u is t squared, and our integral, our dv, is going to be e to the t. Let's go ahead and take it column by column. So let's work with the derivatives. So our first one we have u. Our derivative with our u prime is going to be 2t. Our second derivative, u double prime, is going to be 2. And our third derivative, the derivative of a constant, is 0. Now let's work with the integrals. Now the integrals, you want to pick something that's kind of going to go by in circles or never ending or more complicated. So we have our first, we have e to the t. Our first integral is going to give us e to the t. Our second integral, e to the t. Third integral, e to the t. Now what we're going to do is we're going to multiply across to see which one to have the precise pairing. So we're going to have t squared times e to the t for our first pairing. And then for our second pairing, we're going to have 2t times e to the t. And then for our third pairing, we're going to have 2 times e to the t power. And lastly, multiply by 0, so we're done. Now we also kept track of our signs, which is really nice. So we have our first term is going to be positive, so I have plus. Our second term is going to be negative, and then our third is going to be positive. So the way we would look at it is we would look at it like this, and like this, right? And this is a tabular method, and it's just a quick way to do integration by parts. But again, it doesn't always work. Particularly, our next example is an example where you'll see yourself in a never-ending cycle using the tabular method. And so there we have our answer. So we can say that our answer is t squared e to the t minus 2t e to the t plus 2 e to the t plus c. And that is our answer. Next one. Now this would be a bad example to use the tabular method, but it seems like anything else should be fine in case you want to practice that more. Now the reason you know it's a bad way to use tabular is, let's take a look at it. Let's say we use a derivative in our integral. We use derivative to be sine and our derivative to be e to the x. If we use tabular method, we're going to say the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of sine is cosine, so we have negative cosine, and you're never going to finish. The integral of e to the x is just e to the x, e to the x, e to the x. So you're never going to have a 0 to where you're done with the tabular method. So this is a bad problem. Well, not a bad problem. It's just one that wouldn't work. It's the type of problem that wouldn't work the tabular method. Everything else is fair game. So we have to use our formula for integration by parts. So again, let's remind ourselves what it is. We have our formula is the integration of u dv is equal to u times v minus integral u dv. Right? That's our formula. Okay, let's start off by labeling a u and a v. So for this one, we should let our u be sine. So u is equal to sine of x, and this is the one I'm going to be taking the derivative of. And our integral, the one we're going to take the integral of, is going to be the more complicated one. So we have dv equals e to the x. Okay, let's go ahead and work it out. So we have our derivative of u, du, our partial derivative is du is equal to cosine of x dx. Our integral of e to the x will be v is equal to e to the x. Let's go ahead and replace it so that we have so using our formula, we have our u, which is sine of x, our dv is e to the x, oh, that's not, I'm looking at the wrong part. Next we need v. Next we need v. What is our v? Our v is e to the x. Minus our integral, our u is sine of x. And our du is cosine of x dx. Okay, we see again, we're stuck in a situation where we need to again use integration by parts. You have that there again. Okay, let's use integration by parts. So let's let u be, oh, I made a mistake. Something should have been e to the x. Du, or I wrote it incorrectly. Integral of u of b du. That's supposed to be of b. So then that's supposed to be e of x. All right, let's do integration by parts again. So u equals cosine of x. Our dv is e to the x dx. Let's go ahead and take the derivative of u. So we have du equals negative sine of x dx. And our integral would give us v is equal to e to the x. So we replace it one more time. We're left with minus, just this part here, we just integration of parts gives us cosine of x e to the x minus the integral of e to the x times negative sine of x. Okay, let's go ahead and put this all together. So what is our problem asking? Our problem is asking for the integral of e to the x sine of x dx. And our answer so far is, when we integrated by parts the first time, we had sine of x e to the x, and then we had minus. We had to integrate by parts again, and we got cosine of x e to the x minus the integral of e to the x sine of x. Okay, let's clean it up. Mainly let's clean up those negatives. So I forgot that negative there. So we're distributing this negative to each one. And here we have three negatives. We have the first negative to be multiplied, the negative for our equation, and the negative of the sign. So a negative times a negative times a negative is a negative. We should have a negative for that last term. So that we have the integral of e to the x sine of dx is sine of x e to the x minus cosine of x e to the x minus the integral of e to the x sine of x. Now we see that we're going to be in a spiral again where we're never going to finish. But notice that integral of sine e to the x dx and the integral of e to the x sine dx is repeated. And we have an equation. Equations are super powerful. So we can go ahead, and even though it seems kind of odd, we can go ahead and add that term to the other side to get rid of it. Let's go ahead and add the integral of e to the x sine x dx to both sides. Now that adds to make 0. And here we have two copies of them, a positive and a positive. We have two like terms. So 2 integral of e to the x sine of x dx is equal to what we have developed. All right, last bit. We just want to answer for it, and we have our answer. We just have a constant that we need to get rid of. So let's multiply both sides by a 1/2 so that we can get rid of that 2. So our final answer is 1/2 times sine x e to the x minus cosine of x e to the x. And that's your answer. This one was really fun. If I lost you at some point, you can go ahead and rewind the video, see it again, or you can email me asking your questions. Next part. If we combine the formula for integration by parts with the fundamental theorem of calculus, we can evaluate definite integrals by parts. And you would do it just as you intuitively would think it would work. You're going to take the integral and evaluate until you're done taking the integral, right? Okay, let's go ahead and do this problem. This problem is fun. It's kind of tricky, but it's a fun tricky. Okay, so let's go ahead and label our integration by parts. So we have a tangent, we have an inverse trig versus an algebra, right? Now you're wondering which one should be my u, which one should be my integral, my dv. Well, let's look at our little trick we wrote. Which one comes first? We see that our inverse trig comes first, right? We have logs, inverse trig, algebra, trig, and exponents. So we see that our inverse trig is first, so that should be our u. And that's a good choice for our u, actually. So we're going to let our u be tangent inverse of x, and our dv be x dx. Oh, I misread that. I don't know why I looked at that differently. That's tangent inverse of x. So we wish to do use substitution. Let's take the time to rewrite it. Integral from 1 to 0 of tangent inverse of x times 1 dx. But it still follows the same criteria. We have our inverse trig and some type of algebraic expression. 1 can still be considered to be an algebraic expression. So it didn't change anything. So our dv is just 1 dx. All right, remember one of them we're taking the derivative and the other we're integrating. Okay, so we have our derivative du, tangent inverse of x. It's one of the formulas we listed. I think it's back in section 6.6. So du is 1 over 1 plus x squared dx. And again, this was given from a previous section. We just have to have those handy. Now, the next one we take our integral. The integral of 1 is just x. So we have b equals x. Let's go ahead and use integration by parts. So we have that the integral from 1 to 0 of tangent inverse of x is dx, which is equal to, we have our u, which is tangent inverse of x, and we also have our v, which is x, minus, maybe I should have written the formula so that you can follow. We have u times v minus the integral of v and du. All right, minus the integral of v. The integral of v, we have x, and du. Du is all of this. So we have times 1 over 1 plus x squared dx. Okay, so the first part is already integrated. There's no integral. We can go ahead and label our bounds, 1 and 0. The other one we still have to integrate, and those bounds stay, 1 and 0. Okay, we have to integrate one more time. Now, for this one integration, this one's a tricky one. Let's go ahead and recall one of our ln differentiation. So this is from section 6.4. Recall that d dx of ln of x is equal to 1 over x. So here we have 1 over x. We wish to integrate. Let's go ahead and work backwards. Now we need to use u sub for this one. So let's let u equal 1 plus x squared, and du equal our derivative, which is just 2x dx. Okay, let's go ahead and set up for the integral. So we have the integral, we have 1 plus x squared, and we have x. We're going to need 2x, so we compensate with that 1/2 dx. And when I first teach integration by substitution, I'm very careful. So we said our u is that 1 plus x squared, and our du is going to be that 2x dx. So we can go ahead and integrate or replace it so that we have 1/2 integral 1 over u du, right? And we said the integral of that is ln absolute value of x. Don't forget the 1/2. All right, we integrated with our bounds being 1 and 0. So let's put that all together. So it's equal to tangent inverse of x times x. So I'll put the x in the front. We still have to evaluate 1 and 0 minus 1/2 ln times the absolute value of, oh, that should have been a u because we did u substitution. And we have to replace that u back. So it's 1 plus x squared, with our bounds being from 1 to 0. Okay, let's go ahead and evaluate. So if we plug in 1 for x in the first one, we have 1 times tangent inverse of 1 minus, now we do 0, 0 times tangent inverse of 0. Well, if it's multiplied by 0, that's just 0. And then minus our second, we have 1/2. We're going to plug in 0, so we have the ln of 1 plus 1 squared minus the ln of 1 plus 0 squared. Okay, let's go ahead and clean that up. So we have 1 times tangent inverse, that's just tangent inverse, and we have to see when tangent is equal to 1. Minus, well, this gives us ln of 2. And here we have ln of 1. And when does ln give us 1? It gives us 1 when it's equal to 0, so that's just 0. So we're left with 1/2 ln of 2. Okay, let's think. When is tangent equal to 1? And that's at pi over 4. So our final answer is pi over 4 minus, you can write that as ln absolute value of 2 over 2. Not so bad, right? I recall when I was a student, I'd be caught up on the algebra. So my calculus, so from here and on, would be great. But then when I would do the substitution, I would make silly errors. So be very careful, be patient with yourself, give yourself time to work these out. Don't try to rush. All right, that was section 7.1, integration by parts. It's really fun. It's challenging at first because it's new to us, but with practice, it's really enjoyable. So I hope you enjoy this section. Your homework is 1 through 29 odd. Thank you.